Welcome to the last lecture on magnetic fields. The topic for today is going to be magnetic flux. You might remember from the Gauss's law chapter that we talked about electric flux as being a field times an area element, and today magnetic flux is very similar. And so if we take a look at our diagram over here, we have this blob of material. You notice we have a magnetic field vector going through the material, and if I take a vector that's perpendicular to the surface at any point, and I look at the angle between those two, I can define the magnetic flux, in this case, as the integral of B dot dA. And so you can see, we can write this as B dot dA. The unit of magnetic flux is the Weber. It's just a Tesla meter squared. We have some nice examples of this. First of all, let's do a very simple one. The magnetic flux through a plane. If I have a magnetic field that's parallel to the plane, the area vector, of course, is always normal to the surface, so it's normal to the plane. In this case, B and dA are perpendicular to one another. That being the case, the flux is going to be zero because B dot dA is B times A times the cosine of 90 degrees, which is zero. So that's a very simple example of flux. A second simple example would be if I have a magnetic field that's perpendicular to the surface. That being the case, my area element dA and my magnetic field are parallel to one another. And so B dot dA is just 1. Therefore, my flux is very simply B times A. Now, of course, the more general case is when we have the field and the area vector at an angle that's not 90 degrees or 0 degrees, in which case it's going to be proportional to the cosine of the angle between B and A, which is why we use the expression B dot dA. Do a very nice example on the blackboard of this. You can do the following. It's a little bit more complicated, but it's certainly worthwhile getting exposed to. Suppose I have a current carrying wire, a very long current carrying wire. The wire is going from the bottom to the top on here. And let's say I have a loop of wire out here. And let's say that the loop has a width A and a height B or length B. And let's say that it is some distance C from the current carrying wire. And I want to calculate the magnetic flux from this current carrying wire, or due to this current carrying wire, through this wire loop. Now, the first thing we have to recognize, this is not such an easy problem because the magnetic field that's caused by the wire is not constant in space. So when I reach the loop, the field at this point is going to be greater than the field at this point. So I have a varying field. That being the case, if I want to calculate the magnetic flux, it's going to be B dot dA. In this case, I'm going to calculate the magnetic field using Ampere's law. Let's say for any distance from the wire, we can say that the magnetic field is going to be mu naught times I over 2 pi r, where r is the distance from the wire to whatever space in between this boundary the field lines fall on. Direction-wise, in this case, the magnetic field, since the current is going upwards, the field would be going at all points into the blackboard. When I want to calculate the magnetic flux, then, I'm going to write this as B, which is mu naught, which is a constant, I is a constant current, 2 pi is a constant, and I'm going to use, when I look at the area element of this loop, the area element would be B times A. However, the area is changing. I'm integrating from this point to this point, so let's call this every increment along this width of the loop, we'll call that dr. And so my area element then is going to be dr times the length b divided by r. And I'm going to integrate from c to c plus a. Okay? B is a constant, so I could just as easily pull that outside of the integral. When I integrate dr over r, of course, I get the log of r. So that would give me mu naught times I times b divided by 2 pi, this r has to stay inside, sorry, times the log of c plus a over c. And that is my magnetic flux for this configuration. Notice, of course, it's a dot product, therefore a scalar product, therefore the result is a scalar. So magnetic flux does not have a direction. So you should never talk about a magnetic flux that's up or down or east or west. Unlike a magnetic field, which always has direction, it's a vector, magnetic flux is a scalar. And in this case, this would be the magnetic flux. Learn this example well, because in the next chapter, when we talk about Faraday's law, we're going to be using, in fact, changing magnetic fluxes with time. And so this kind of example will be useful, and we'll build on it. Well, this leads us to the third of our 4 Maxwell equations. The first one we did was Gauss's law for electrostatics. The second was Ampere's law, which is not quite complete yet. We'll modify that. We'll show you how Maxwell modified it later on. But right now we're going to talk about the third of the 4 Maxwell equations. That's Gauss's law for magnetism. And it's a very simple law, because what happens is that because magnetic fields don't begin or end at any point, magnetic lines are continuous and they form closed loops. That means the number of lines that enter any surface is going to equal the number of lines leaving the surface. Therefore, Gauss's law of magnetism very simply says that the magnetic flux through any closed surface is going to be 0. In other words, Gauss's law for magnetism is just B dot dA equals 0. Well, the implications for this are pretty large, in that because I don't have any discontinuities in my field lines, that says that you can't get an isolated magnetic pole or magnetic monopole. They haven't been detected in any case. According to Gauss's law for magnetism, they wouldn't exist. That doesn't mean that they can't exist, it just means that nobody's ever found one yet. Should we find a magnetic pole somewhere in the universe, and as I've said before, the standard model says that they can certainly exist, at least there's nothing that forbids them from existing, that would change this equation to some magnetic charge on the right-hand side, but for now and for all intents and purposes, everything we've observed says there are no isolated magnetic poles or isolated magnetic charges. Therefore, Gauss's law states that the magnetic flux through a closed surface is going to have to be 0. You have as many lines going in as you do going out. And so that's what we want to say about Gauss's law for magnetism. Now you have 3 of the 4 laws. The last one that we'll do will be Faraday's law in the next chapter. I'd like to change gears and let's talk about a more microscopic view of magnetism. And then move into descriptions of three types of magnetism that we can talk about: ferromagnetism, paramagnetism, and diamagnetism. But for now, let's motivate this by talking about magnetic moments. So in general, any current loop is going to have a magnetic field and will have a magnetic dipole moment. So we could even go down to the atomic level and talk about current loops even in models of the atom. We're going to use this to describe why some materials or elements have strong magnetic properties while others don't. So in the classical atom, we have the following explanation. This is not really correct, but we'll just use it for now. Electrons moving in circular orbits, the planetary model of the atom is not correct, but we can use it as sort of a rough model for at least our purposes right now. Because we have a current moving in a loop, that's like having a tiny current loop. And so with that, we can associate a magnetic moment for the electron. Magnetic moment is the current times the area of the loop. And so that would be a vector that is perpendicular to the path of the loop. Pointing in the opposite direction is the angular momentum of the electron. That's what we use the vector L for. Because the electron is negatively charged, the magnetic moment and the angular momentum are going to be in opposite directions. So that's a current loop and a magnetic moment. Again, it's a simple model because we're assuming the electron moves with a constant speed, has a constant circular orbit of radius r, travels a distance 2 pi r in some time interval t, and so we can talk about the current is just the charge, velocity of the charge divided by 2 pi r. That being the case, we can write mu, the magnetic moment, as we said, is current times area. I can also write that in terms of this expression as 1/2 times e times the velocity, or the speed, times the radius of the motion. Because we can write angular momentum for a point particle as mvr, for a point particle, like an electron. Therefore, I can express the magnetic moment in terms of the angular momentum as well. It's just the charge of the electron divided by 2 times the mass of the electron, all multiplied by the angular momentum. So there's a nice relationship between the angular momentum of the electron and the magnetic moment. As we say, the vectors point in opposite directions because of the negative charge of the electron. As you study deeper into physics and we learn more about quantum mechanics, we'll realize that angular momentum is quantized, and that will be kind of an important concept when we do quantum physics. Now, in most substances, while you may have many, many electrons, most of the magnetic effects cancel one another. So what typically happens is that the net result for a magnetic effect is that the orbital motion of the electrons is going to be very small. And generally only one electron out of a multitude may have any effect whatsoever. So that being the case, we can explain why many, many materials are not magnetic, whereas other materials are. And really only a small fraction of materials are. There's another quantity that relates to this, and it's called the spin of the electron. It's an intrinsic angular momentum. The electron isn't really spinning. This is just a term that we use. again, based on the planetary model of the atom, which of course is incorrect, where the thought is the electron would be spinning on its own axis, which is impossible since the electron is just a point. Nonetheless, the term spin stuck. It is an intrinsic property, and it behaves as though it had its own intrinsic angular momentum. It can be better described using relativity, but we're not going to do that in this class. We can talk about the electron spin, though, as providing an angular momentum equal to the square root of 3 over 2 times Planck's constant. Planck's constant divided by 2 pi. Planck's constant is 6.626 times 10 to the minus 34 joule seconds. And h bar is that divided by 2 pi. We most often use it in the h over 2 pi configuration. The way the electron spin and the magnetic moment of the electron are related is the charge of the electron times twice the mass, divided by twice the mass of the electron, times Planck's constant over 2 pi. This constant for the electron is called the Bohr magneton, is equal to 9.27 times 10 to the minus 24 joules per Tesla in our SI units. And we can put up a chart of some electron magnetic moments that are attributed to particular atoms or ions. So for example, hydrogen has a fairly large magnetic moment. Helium and neon have 0 magnetic moments. And then you have larger ones, cerium and so on, erbium. And the fact that we have non-zero magnetic moments leads to magnetic properties. So for example, elements with unpaired electrons will show magnetic properties. Strong magnetic properties, we call these ferromagnetism, ferromagnetic materials such as iron, cobalt, nickel, gadolinium, dysprosium, and some others as well. Typically, if you have a magnet, an element such as this, the magnetic field is very strong. If you put this particular element in a magnetic field, you will align the magnetic moments of that element. But the interesting thing about this is if you turn off the magnetic field, the magnetic moments still stay aligned. So the substance retains its ferromagnetic properties even if you remove the magnetic field. That's what distinguishes ferromagnetic materials from paramagnetic materials. When we talk about regions where the spins are aligned, we call those regions domains. And you might have different sections of the material aligned in different directions, which means that you have domain walls between those sections where you have strongly aligned. You might have a bunch of strongly aligned spins in this direction in one region of the material, and then you may have another part of the material where they're aligned this way, and so on and so forth. Not all of the spins will be aligned exactly the same way in the entire material, but you'll have these domains where the alignments take place and will be separated by domain walls. This is a characteristic of ferromagnetic materials. If the material is originally unmagnetized, we see that the dipole moments are completely randomly oriented. And so if you were to calculate the net magnetic moment, because you have so much randomization, the net magnetic moment would be 0. However, if you place this material in a magnetic field, what you're going to do is find that the domains start to align themselves. So this is an external magnetic field applied to this magnetic material, this ferromagnetic material. We see that the size of the domains will grow. You see the alignment is fairly strong. Now, once you turn off the field, it's going to be the case that the material will retain its magnetic field. And so the question becomes, does it always work like that? The answer is yes, until you reach a temperature that's excessively high. We call this the Curie temperature. If you exceed the Curie temperature for a particular material, for example, for iron, now you're going to lose your ferromagnetic properties. The material becomes diamagnetic. What's actually happening at that point is the material is undergoing a phase transition from the ferromagnetic to the paramagnetic. As you'll see, paramagnetic materials lose their magnetic properties once they're removed from a magnetic field, unlike ferromagnetic materials which retain those properties. And so we call that a Curie temperature or a critical temperature, where the material becomes paramagnetic when it's heated above that temperature. And as you can see, we have a table of Curie temperatures for ferromagnetic materials. See that with iron, it's 1043 kelvins, cobalt 1394, and so on and so forth. That also would probably convince us when we think about the interior of the Earth. That it's a misunderstanding to say that it's the fact that the core is solid iron that causes the Earth to have a magnetic field. That's not correct, because the interior of the Earth has a temperature that's far above the Curie temperature. So iron, solid iron, would be a paramagnetic substance at best. What causes the magnetic field of the Earth is the motion, the sort of currents of liquid charged particles. Those little currents are causing magnetic fields, and the Earth's magnetic field is a modest, about half a Gauss. So it's not a very large field. When we talk about paramagnetic substances, they have small magnetic attraction, or we call it positive magnetism. It results from atoms that have permanent magnetic moments, but the interactions are weak. And if we can place this substance in an external magnetic field, you can align the magnetic moments up. But as I said, once you remove the magnetic field, the magnetic moments will randomize again, and then the magnetic field will be zero. Magnetic effects will be zero. The third type of magnetism we can talk about is a substance that has a weak repulsion in from magnetism. The moments induced in a direction opposite the magnetic field. That's what we call diamagnetic substances. So they're weakly repelled by a magnet. And so you're not going to detect such an effect unless there's zero ferromagnetism or paramagnetism present. And so one nice example, though, of diamagnetism is in solid state physics or condensed matter physics, where we talk about superconductors exhibiting the Meissner effect. The Meissner effect is what happens if I bring a permanent magnet near a superconductor. You'll see that the magnet is actually repelled from the superconducting material and undergoes what we call magnetic levitation. It's kind of a spectacular effect, and it's an illustration of diamagnetism. And that's all that we've got to say. If you want to study more about ferromagnetic effects, paramagnetic, diamagnetic, and so on, condensed matter physics or solid state physics course is where you want to go. That's where these things are discussed in great detail. For our next lecture, we'll be talking about Faraday's law and the fourth equation attributed to Maxwell. Thank you.